The p-value in common hypothesis tests is computed by choosing a test statistic, computing a value of that statistic for the sample, comparing that value with the sampling distribution of the statistic, and calculating the p-value from the area in the tails of the sampling distribution. The test statistic could in principle be any statistic that gives a measure of the difference between the sample and the null hypothesis and that has a known sampling distribution, but for common hypothesis tests there's usually an established test statistic that meets all of these requirements. For example, starting with a sample similar to the samples used in previous sections and a null hypothesis that the mean of the population from which that sample was drawn is 1,000, one possible test statistic is simply the difference between the sample mean and the mean specified in the null hypothesis. The problem with this test statistic is that if the standard deviation or the variance of the population is unknown, then the standard deviation of this sampling distribution is also not known. If the population is normally distributed, which is an important condition in this calculation, then this sampling distribution will be a normal distribution. The p-value is the probability of getting a sample for which the test statistic is as far or further from the test statistic under the null hypothesis in either direction than the test statistic of the sample that was collected. So the p-value is the area in the tails of this distribution. But without knowing the standard deviation, it's impossible to know the location of the test statistic in this distribution or calculate the p-value. This problem is solved by considering a different statistic called a t-statistic, which is defined as the difference between the sample mean and the mean under the null hypothesis divided by the standard error SE of the sample mean, where SE is the standard deviation of the sample divided by the square root of the sample size n. The value of the test statistic for the sample can be computed by calculating the mean of the sample and using that value in the formula for t. The advantage of this test statistic is that this sampling distribution is a known distribution. Assuming that the population is normally distributed, this distribution is the student t distribution with n-1 degrees of freedom. The p-value is the area in the tails of this distribution, which can be computed using the cumulative density function CDF. This is also the p-value returned by the t-test function for this sample and the hypothesized mean of 1,000. The assumption that the population is normally distributed is one of the conditions for the validity of this calculation. The complete set of conditions is the same as the set of conditions that came up in the earlier section on confidence intervals for the mean of a population. These are the conditions necessary for getting a sampling distribution that matches a known distribution, and that sampling distribution is needed for computing the p-value. The population must be approximately normally distributed so that the shape of the sampling distribution is a student t distribution, or the sample size must be big enough that the sampling distribution is approximately a student t distribution anyway. The sample should be representative of the population and not biased, which is a requirement for almost all statistical analysis, and the population should be at least 10 times as big as the sample so that it is possible, at least in principle, to draw many random samples without having the same individuals in every sample. Before closing, specifically regarding the condition that the population be normally distributed, hypothesis testing functions like the t-test function include various tests for normality and can generate a warning message, such as the warning message produced by this input, if one of those tests indicates a high probability that the population from which the sample was drawn is not normally distributed. These tests of normality are themselves hypothesis tests, and like any hypothesis tests, these tests can return false positives. So this warning message does not by itself mean that the result from the t-test function is invalid, but the warning message does correctly suggest that it may be worth looking at a histogram of the sample or otherwise considering more carefully whether the population distribution is close to a normal distribution.